Howdy, everybody in YouTube land. What we have in front of us today is a Fluke 660A/AN, which is a 10 kilohertz to 520 megahertz RF signal generator. So, the thing with this is, I've been needing a signal generator for a while because I like to do AM radio alignments and FM radio, IF stage, things like that, right? Plus, there's some demodulation stuff I want to play with some bespoke equipment and, little things like that. Now, of course, everybody goes for that traditional 990 megahertz or more HP one that you see, but they're so expensive, and that's why they're very hard to get. But I've been wanting one for a while. Now, this one, for some reason, these things go for really cheap. In fact, the shipping on this costed more than the unit itself. I think all in all, I'm in at $100 with the shipping, and the shipping was the majority of that. It was really cheap. But I don't know why this one doesn't have as much of a demand, and why, who knows? Maybe it's just reduced feature set, or it's just lesser known. It's a fluke. I mean, and the thing is, with this particular one, it won't do like a sweep or anything like that. However, it still supports the AM, FM modulation and deviation adjustments and stuff like that. So, in theory, you could do a sweep with this. It would be crude, but you could, because you could set the center frequency of your sweep and then just do external FM input, and your amplitude would be your deviation, and the frequency would be the sweep speed. So you could technically do it with a secondary generator, sine generator. Anyways, point of the story is I needed one of these for a while. Now, this one does have a problem, which is probably why it was so cheap. So if I turn this on, it digitally seems to work fine, and it has a VFD display. But we're flashing this uncal light, and I don't know what that actually means yet. RF output off or on. So I can say modulation 30, we'll do internal FM, whatever. 300 megahertz, so we're going to set the frequency to 455 kilohertz, which is very common frequency that we're going to use. We're going to set the let's see, the output level. I'm pretty sure. Let's see, dB. No. I don't know. Amplitude. So we're going to set it 0 dB. Alright, so this thing, in theory, should be producing a signal. So if I turn this oscilloscope on, we should have a 455 kilohertz RF signal on that scope. Now, unfortunately, I do not have a connector for this. I think that's just an N connector, so nothing special. Dang it. Alright, so we're in there. Nothing. So this thing has no RF output, and it keeps flashing the uncal light. So also, when you turn this off, it resets back to the default 300 megahertz and all of that. So I'm wondering if this has a Dallas battery in here that's dead and it's lost its calibration settings. I'm not sure. Maybe there's capacitor issues. So let's crack this lid open and take a look at it and see what we're dealing with. Whoa, this thing is cool on the inside. It looks like it's from, with the date codes I see, it's like 1985, 1986, so this thing's old. I didn't realize it was actually that old. That's kind of impressive. I would say impressive that it still works, but it doesn't. So, oh man, it could be literally anything. So this predates capacitor problems. So, at least not like leaky through-hole electrolytics. So, I'm not sure what's going on with this one. Oh yeah, here's a funny story too. So, we're in the middle of this hurricane. We've got all these winds here. We've got the pouring rains, flooding rains. We've got the state of emergency. The roads have a travel ban. And even as the making of this video, there's still a travel ban from the crazy storm. But this county is basically up and running at this point. But Asheville is not, and it won't be for years. Anyway, so because during all of this, it's pouring rain out. I'm sitting with no power, and I'm concerned about floodwaters coming in, and UPS delivers a package like, here you go. I just think it's funny. I think it's funny. It's like imagine being on the coast in a hurricane and floodwaters are coming in, the power's out, and UPS runs around your neighborhood. It's like, well, here's a package. I don't know. I just find humor in it. It's funny. So okay, but it looks like I'm gonna have to take the bottom off as well because I really can't see anything in here. So I need to take the bottom off. Wow, you can't get in from the bottom side either. Holy crap! This thing is well shielded. I don't know if I want to say it's over engineered because some of that HP stuff is too, but this is critical precision equipment, so I suppose it makes sense. I tell you what I am going to have to do is I'm going to have to find the service manual for this so I can look up voltage charts and stuff like that because maybe we have a voltage issue, a broken solder joint. Who knows? Who really knows? Well, it looks like it's got a GPIB board in it that's dedicated for this. John Fluke. Yeah, how do I get in this thing? Actually, you know what? There's some resistor. I guess these are adjustments. I don't know. Actually, this shield is separate, so you can take this thing apart. Yeah, here's a calibration sticker here, and it's never been apart. That sticker has never been breached, so nobody's been in here. And I'm kind of, since this is the RF, is this the RF section? I don't know. I'm kind of reluctant at just going in there just to go in there, unless I absolutely have to. I mean, you know, I might as well for the purposes of this video anyways, because it doesn't work. Wow, this has got to be one of the coolest boards I've ever seen. This is gonna be a nightmare to figure out, but wow, some of the impedance network design, it's crazy. It's kind of fascinating. They're probably doing this. Oh man, to be the layout engineer on this thing, because they'd almost have to be doing that for impedance reasons, load reasons. Like these are just forms of inductors, especially things like this, you know. Oh, we got some digital logic down there with some analog stuff. We have this here. What is that? Control voltage from something. Synthesizer. Oh, it's a test point. Between 2 to 25 volts. Oh, yeah. So we've got some things to... modulation oscillator levels. Test point for that. Am depth. There's all kinds of things we can do here. So it looks to be well documented at least. So since we have no output whatsoever, just got the top one off and oh boy, I think I found the problem. Maybe not the problem, but a problem. That little tantalum capacitor went boom boom booms. It's probably the same as these two over here. Yikes. Well, that explains that. But I did notice there are no electrolytics in this board whatsoever. Actually, nope. I am wrong. There's one here and one there. And two over here. That's weird. They took a hybrid approach. But that right there, that is a major issue. So when that blew up, did it blow a fuse with it? Are there fuses back here? Ooh, there's some TO3 transistors back here. I'm gonna have to check for voltage on those. Actually, positive, and there's a positive 15. That's going right there. That's gone. There's positive 15 and there's negative 15. So we do have some test points that we can look at. All right, so here we go. Let's check the Fluke with the Fluke, because why not? Sounds like a fluke to me. Alright, so we're going to power you back up and see if we have the same fault as before, and I think we will. Yeah, uncal. Alright, so the affected one, since this is the 15 volt supply, let's check you. Actually, that one's good. Let's check the minus 15 volt. Oh, well, that's a problem. Okay. We don't have any voltage here. But if we follow this trace, it goes right to another one of these tantalums. So you know what I'm going to do? I'm going to put this on diode check mode. We're going to check you there. Not great, but not shorted. Let's check the minus 15. Ooh, that's bad. Okay, so we've got a short on the minus 15 volt rail. We have another short here too. Actually, no, maybe not. I'm just checking this cap here. So we follow this one. Yeah, this is... Considering this looks to be of the same as that one, they're probably toast. Which means I bet these likely are as well, or will be. It's the typical tantalum IBM time period. Because remember, IBM PC XTs and early ATs from the same time period have the same exact problem. So those, yeah, we're going to have to pull this board and figure it out. Also, my other concern is this minus 15 volts. We need to figure out where it runs off to, because I'm assuming it's coming up from the bottom, and the 15 volts probably comes up to here somewhere, and it's popped a fuse. I have a feeling it probably has popped something over here. But hey, I don't actually know. I'm just guessing. I still haven't pulled a service manual yet, but I don't need one to tell me that that is fucked. But I will need to pull this board. So now it's become an all-out thing where I'm on the hunt for tantalums. So this one does not have any tantalums on it as far as I can tell. This one does. So I think what we're going to have to do is recap all of the tantalum capacitors. Because sure enough, I removed this board and the short went away right here. It's not there. So it's this other tantalum here that's decided to short as well. So now with the short removed, I need to check and see if my negative 15 volts comes back. Because if not, then it's damaged the power supply as well. But yeah, all these tantalums, oh, I even see some down there. They're going to have to go because they're all going to have this problem. So I have to get a list of caps and get them replaced. And I don't know why they use tantalums, because it's like on some of these they use electrolytics, on others they use tantalums. Maybe it's for temperature compensation. I'm not sure. That's weird. I think it also did damage the power supply because here's our power inputs over here. We got nothing over here now. But we also have power supply inputs here. So from here we have 37 volts, which appears to be right. We have positive 15. This should be negative 15. We got nothing. And then 5. Okay, so it damaged this power supply, so it's going to have to come out. Oh man, this thing is a nightmare to work on, because I got to get all of this apart, and I got to inspect every single board for those stupid capacitors. It's the bane of my existence, because it's either leaking electrolyte capacitors or it's shorting and blowing up tantalum capacitors. It's one of the two every single time. I'm just peeling it back one layer at a time. I moved that board off the top. That reveals the microcontroller board here. It uses a TMS 9995. I'm not even sure what that one is. All these ROMs. Now I should dump those just to have them on hand. What I don't see is any type of retention memory. So maybe this thing just doesn't have it. I don't see a Dallas chip. I don't see anything like that. So maybe this type of machine doesn't use it. But attenuator. Oh, weird. So attenuator. There should be the main ROM. Output ROM. VCO ROM. Something. Attenuator. This must be the main system ROM here. I'm going to dump them all anyways. None of these chips are in a socket except for these two here, which is also just as strange. But yeah, I like the attention to detail. Pull tabs. So anyways, I'm peeling it back one layer at a time because, look, we got one here, we got one, a couple of there. These little tantalums are all going to have to go because they're going to short otherwise. But I still have to unbury that power supply somehow. All right, so I got a clearer picture of what's going on here. So these pins come up from the bottom. Those are your power supply pins. And then those two that we're measuring over here, that powers this little side of the board here. So I was taking measurements on the other side where the capacitor was blown up next to these two pins. Well, these two pins supply power to this board, but the power actually comes all the way from over here. So that makes sense. So this purple wire is dead. And the purple goes right here in this very end connection. And I don't know where it goes from there, but this board's got to come out anyways because these tantalums have to go. So, I don't know how that's going to come out because this whole piece has to come off to get to that point, which means all of these have to come off, and there's screws through there and through here on both sides. Not to mention there's these cables that wrap around and go around the primary wire cable, which comes in here, and it goes to, well, crap, it's going to this Molex connector. So I can probably get this board out if I can get it to swing this way. Oh man, what a pain. What a pain. Oh, the room might be a little smoky. I finally got this out and I was probing things and I lost another tantalum right in my face. Oh my god. Alright, so we'll start with this one since this was the one that was the hardest to get to. Yeah, that one went on me when I was trying to find that negative 15 volts because I unplugged everything and I was seeing if the negative 15 volts was there. And then this exploded, stunk the room up, so I cut it out, powered it up again, and then started checking voltages, and I noticed my negative 15 volts is there. So, however, that comes from this tantalum. So I don't know. We'll see. More importantly, we need to just go ahead and get all these tantalums off this board and recap it. Now, I do not have any tantalums on hand. So I'm just going to replace these with electrolytics. It'll work fine. Much better. Are these better than the tantalum ones? No, not by a long shot. Excuse me. But it's better than what was in there because, yeah, that one there especially, it went on me during testing. Alright, so I got all the caps in that one. I'm going to go ahead and start moving through all the other boards. I think the next board I want to work on is the one that's really bad. That one definitely shot out some serious flames because it even melted the little pull tab that pulls the board. Wow. What I need to do is measure you back up to over here and make sure there's still a path through the circuit board. Because when this shorted, it could have blown up a connection back here. I don't know. But I need to check that. But also, these are got to go. So these are 82 microfarad at 25 volt. I'm just going to put hundreds in there. It's just easier. Starting to work my way through this board. And I was able to clean this section up pretty darn good, I think. So that's taken care of. I ran into a situation over here. That's a 15 microfarad because so is this one. And I put a 22 in there because that's just a decoupling capacitor for the power rail to this op amp. This one is part of this resistor there. These are timing components for this monostable multivibrator, so I can't just change out that with a different value, like a 10 or a 22, without recalculating out the resistor to keep the timing the same. So I decided not to mess with that one because the voltage across that's going to be relatively low anyways. So I've been slowly working my way across the board here. Now I still have these left. Look how fried those are. I mean, whoo, bang. But yeah, all of those are the 10 microfarad. There's a 10 microfarad 50, two 10s at 35, and a 10 at 20. And they're kind of fried looking, so they're going to have to go as well. All these tantalums are going to have to go. I still have one over here too. But yeah, slowly working through the boards, and everything is turning out all right so far. Well, that board's done. I think. Oops, I think I forgot one. Never mind. These little orange guys are easy to forget. So I have U, maybe. It depends on what part of the circuit that's in, and if I have that value. This one I can't do anything with, but I think all the rest of them is replaced. Nope, I got one over here. So I got two that I missed. Alright, so two. Yes, two. One, two. Okay. Try again. Alright, so I had to leave this one too because this is a 6.8 and I don't have a 6.8. And it's in series with the resistor, so this is an RC filter in the signal path somewhere. So I'm going to leave that one alone as well, just like with that one. And if they go bad or short, I'll change them. But right now I'm just going to leave them. The rest of them have been changed. Let me go over it again and make sure. Oh, it looks like it has. Everything's been changed. That's important anyway. So, all right. Let's set this board out of the way, and let's grab the CPU board because there's only a couple on there. All right, so there's the CPU board, and actually, I kind of want to dump the ROMs too while I have this out. So this one has a different manufacturer, it looks like, than that one. But so far, I only see 3 of them. So those are the ones we're going to change on this one. There's only 3, and they're going to be decoupling capacitors. There's nothing special going on here that matter. When recapping this board, you've got to be careful because the board is not physically marked where the positive side goes. So I had to physically mark the board myself. Board out of the way. Now we have to move on to this one. And this one's interesting because this one has electrolytics in here, but has tantalums over here, and all the other ones had tantalums, or a little bit of a mixture. Anyways, so this one, it's the same ordeal. We have polarized capacitors, but we don't have any marks on the board what the polarity is. So I have to mark that first and then remove them so that's not lost. Well, that just about covers all the tantalum capacitors at the moment. So I'm going to go ahead and put this thing all back together and see what in the world happens. It's either going to work or it's going to need further troubleshooting. I'm hoping it's going to work. But there's our casualties. You can see so many of them. That one's blowing up. That one's gone. That one's gone. That one's gone. Well, that might be remnants because these two were next to each other, but all the rest of them weren't. So, yeah, that's pretty bad. It's like, I don't know what it is, but these early tantalums are made of a material when they short, it just goes full on explosion mode. As I'm working on this thing, one thing I wanted to point out, I just recently saw a picture of, and that is there's a newer version of this one that actually does have a Dallas module that sits right here with the Dallas clock chip on it. But this one doesn't have it, and the standoffs don't even come all the way through, or the header pins. So this model does not have it, but the newer version does. However, this board is primarily the same between them. So, alright, I don't have the shields in place yet, so this thing is probably not going to work perfectly. But I think I have enough. I gotta get the GPIB board installed, but I think I have enough where I can actually power this thing up, check voltage rails, and test it. Alright, so here we go. It's either gonna blow up or it's gonna work. Well, that looks good. No uncal. Oh boy, I think we're good. Let's do internal AM modulation. Let's do frequency 455 kilohertz. All right. Uncal came on. Darn. Well, it kind of worked. Well, I have the uncal light flashing again, but maybe I have voltage. Well, let's see. Did we get anywhere or did we not? Let's see here. We have our positive 37 volts, which we do. Positive 15, we have it. Negative 15, we have it this time. 5 volts, we have it this time. Let's check up here. where the damage was. 15 minus 15. So we have voltage now where we didn't before. So now it's possible the uncal light is on because there's no shielding in place, but let's get this oscilloscope in place and see if we have anything whatsoever. Actually, we'll do frequency 455 kilohertz because that's going to be the most important frequency this thing ever uses. Alright, so here we go. Do we have anything at all? Ooh, I have RF. I do have RF, so let's change the amplitude. Only goes to 19 dBm. Well, let's see. I gotta change the trigger level because it's just not. Wow, we have 455 kilohertz. It's actually working really, really well. So we have. Let's turn off internal FM. Yep, we got internal FM. We have. AM doesn't work. Nope, internal amplitude modulation does not work. But FM does. But AM does not. Amplitude modulation. Let's see. Turn the modulation all the way up. 100% modulation. I mean, it's working. It's just not very... Alright, so there's still a few issues here, like this amplitude adjustment. Now, the problem with this amplitude adjustment, it's not changing anything here until you hear a relay click. See? It's only... The stepped attenuator is the only thing working. The actual DAC isn't working, so I need to look at... Yeah, I've got a lot of different troubleshooting to do. That's probably why it says uncal, because the amplitude circuitry is still not working properly. Alright, so it's time to break out the service manual, and just from a quick glance, it says the level control is provided by two separate circuits, a step attenuator and a DAC. We know the step attenuator works, but the DAC doesn't. And you can just kind of skim through that and read it if you want. And then it says the amplitude modulation, the output level of the DAC is the ALC loop control voltage. The generator output is amplitude modulated by varying this voltage, which means, remember, the amplitude modulation does not work too unless I turn it all the way up. So that means this circuit is not working. The DAC might be, but the DAC's output is part of this, and that circuit is not working, so we need to find out why. Here's something fun. I ran it all the way up to 300 megahertz, and if I adjust this dBm amplitude, I can see it bounce up on my thing. Now, this scope won't see 300 megahertz, but it's doing something. And I don't... Well, I guess the uncal light is on, but it's not flashing. So frequency 100. Now it's flashing. So if I change the amplitude of that one, yeah, nothing happens. I mean, I can see the frequency coming through, but it's weird. But I get the same uncal light, so frequency 500, because it'll go to 500 megahertz. Same thing. Frequency 400. No more uncal light. Yeah, you can kind of see something going on. Anyways, so here's another thing I find interesting. 300 megahertz, which is above 245. I can even just do 245, because 245 is a magic number in the service manual for this circuit. Everything's fine. There's no errors. But the minute I bring this amplitude... Whoops. If I bring this amplitude up, I get a 2 status, down 0 status. So I'm starting to wonder if when I lost the minus 15 volt rail through the short of tantalums, if it didn't blow a chip up on the output attenuator board somewhere. I'm not sure. Something is definitely up with that. Alright, I think I found our problem, or at least the general problem. So right now I'm at 245 megahertz at negative 9 dB and there's no faults. Now if I turn this up past 13 there is a fault. But that's because I guarantee this thing has to be terminated at 50 ohms, and that might be why. So I'm going to ignore that for now. And if that's still a problem, we'll deal with that later. Right now, I want to work one problem at a time. And our problem is this machine has 3 bands. And here they are. We have band 1, band 2, and band 3. All right. So 245 is the magic number, like I said earlier. So if I go down to band 1, that's when I get a fault and I can hear the fan pitch change. It consumes more power. So whichever is getting turned on, it's causing a ton of draw. Okay, so we know the fault is in band 1. All right, so let's check band 2. So we're going to go band 3, 349 megahertz. So this is still band 2, and if I go up, now we're in band 3. Still no fault. Alright, so we don't have a problem with either of those bands. So let's do status 0 across the board. We're good. So we're going to go back to 245 megahertz, down 1, and now we have a fault. Status unleveled. So we have a problem with that. So if we look at the schematic here, I printed the schematic off separate from that. All 3 bands are switched from this 273 latch right here. And they're driven into these like TL84 op amps and these transistor arrays. So all of that shoots off to these low pass filters and things like that. And then this table tells you when you select a certain band, like MIDL goes high, and then HETL goes low, and then this goes, so these will switch around. These 2 switch states, and I don't have a problem. These 2 stay the same state, and these all switch states. So it could be with these 2 bands being 1. I mean, it's hard to say. It's entirely possible that one of these is stuck. So what I'm trying to do is find a commonality, because these 2 bands don't have a fault. These two switch states in that band, and it's the only one that does. So I know this one's fine. But it's the other 3 I don't know, because this could be stuck at 0. Actually, this could be stuck at 1, so when you flip over to this one, it'd give you 1 across the board, which is an illegal state, right? This could be stuck at 0, but if that was the case, then the middle band wouldn't work. You know what I mean? Same thing here. So this one or this one could be stuck at 0. This one could be stuck at 1. So I need to take a look at that. And that's MIDL and HETL. That's these 2 lines right here. So I need to check all of that, because remember, we lost one of our rails. It's possible that any of these is shorted and we're having a problem there, but we'll take a look at that. My phone's ringing, so give me a minute. Definitely the superhet stage that's not working, because if I'm looking at the detector diode voltage, 0.63, 500 millivolts per division, that's about right, because we are in the mid band. As soon as we go into the low band here, we lose it. See that? So, and then when we go in the low band, let me zoom this back out. When we go in the low band and we lose it, we get the uncal light. So the mid band and high band is working fine. Like I can go to the high band right now, 500 megahertz. High band works fine, no errors. So 245 goes right back to the mid band. And as soon as I go down 1, takes us to the low band, and I lose the pulse or the output level from the detector diode. So that tells me that somewhere in here it has, not in this one. Hold on, this is the wrong one. Because there's a detector diode input. The test point I'm checking is right there. So that is working. The issue is right here. This superhet circuit, which is these two blocks right here, is causing our problem. Now, I've already tried to heat these capacitors up to see if I had dried out caps causing the problem, and that's not what it is. And I'm definitely getting gain through this stage. I don't know if I'm getting the right gain, because I don't know what that is. That's not specified in this manual. But I am getting gain through it. But I've got almost nothing detectable from the mixer stage, which is going to be hard to do anyways at 245 megahertz because, that's not going to work there. But if I say 455 kilohertz, again, we are way, way, way down. So, but a 455 kilohertz can be detected from that. But we've got an 800 megahertz local oscillator frequency coming from the synthesizer, and then it's mixed with the frequency that comes out of this module here, which is a variable frequency oscillator, somewhere between 0.49 to 1 gigahertz, thereabouts. So that is working, because when I do get a frequency out of here, even though it's very low, it is accurate, which means the synthesizer board is functioning. The VCO is functioning. But this circuit here I guess doesn't have enough gain, because the leveler circuit, which is this here, and that goes back from, there's the leveling control from the DAC, the digital analog converter, which is right here and here, is driving this thing normally, like it's supposed to. But there's a DC offset here that's way the heck out here because it's it's too low of a level. So that's our issue. There's some gain issues going on in there, and I'm not sure why. Because I did a static check of these transistors and also these, and they're good. Don't know if they're leaky, but they aren't shorted and they're not open. So while I systematically troubleshoot this piece of equipment, I wanted to explain this circuit a little more, especially this one here. So if you look here, we have all these random diodes, and then it looks like we have RF going this way and this way at the same time. They're all connected together and all that. Well, actually, they're not. These diodes are not your standard diodes. These diodes are what's known as PIN diodes, or PIN diodes. What that actually means is these have a standard forward PN junction where it blocks DC one way and passes DC another way, just like any other ordinary diode. But it does have an intrinsic property that when these diodes are forward biased, it will allow RF to pass over the DC bias point, because technically it's a DC bias, but it will allow RF to pass right through that diode when it's forward biased with a DC voltage. However, if it's reverse biased with a DC voltage, it will block the RF. Okay? It's a switch, essentially. So now that we know that, let's study this circuit a little bit here. When we're using at 244 megahertz and below, this voltage coming in right here goes negative 15 volts. Goes negative. What does that mean for this circuit? Well, let's explain. This point goes negative 15 volts. You get about a negative volt here, which makes sense because that's your diode drop. Well, that point is going to be lower than this point, so this diode is now forward biased. So RF will come out and go right through this diode in this direction. However, that same negative 15 volts is going to be here as well as here, because there's three tied together, right? This will also be negative 15 volts. Well, actually, it won't be negative 15 volts. It'll be like 0.1 or whatever the diode drop is. Point is, this is going to be negative, which means this guy is reverse biased. So this will block the RF. Same over here as well. But this diode and this diode are the same exact configuration. So this one will be forward biased. This one will be forward biased. So RF will come through here, go through there, and back down to this point here and out that way. It won't go this way, and it won't go this way. However, there's a chance that some RF could leak on this line, which is why we have these 4 diodes. So when these two are reverse biased, these are forward biased because this point is going to be lower than this point here, which means all 4 of these turn on and RF will shunt to ground. So it blocks all RF on this line. So the only thing you get through here are leakage currents, whatever that might be. So that's how this switching network works. Exact opposite happens when this thing goes to a positive 15 volts. What happens when this goes to positive 15 volts is these two will forward bias, these two will reverse bias, and those 4 will reverse bias. So these will block the RF, so it shouldn't go to ground. And we do get that behavior because when we go into the 245 or above, notice we don't have any faults and everything works. Now, I don't know if the decibel level is correct because, again, I don't have equipment that will measure this thing at that high of a frequency, nor do I have a 50 ohm dummy load. I need the proper equipment to be able to make sure that the dB output reflects what is being shown on screen. So that's how you know if your stuff's right or not, and there's some limited ways to adjust it. But anyways, so we know that's working, but it could be stuck going in one direction only no matter what. So I monitored this signal, and this signal is switching. Negative 15 when you go below 245 and positive 15 when you go above. That's normal. So the digital control logic is working. And I have proper diode drops at these 3 points, which means these diodes are, and at least from a DC standpoint, are working correctly. That doesn't mean that there isn't some leakages or some other weirdness going on with these diodes that could be shunting some of our RF over here to ground, or we're path where it's splitting both ways when it's not supposed to, and maybe that's why our circuit's malfunctioning. I don't know. Not very likely though. These pin diodes are extremely reliable, and that's all of these diodes right here. These are all pin diodes. So we have that. So that only leaves really 2 things. We have a mixer problem where we're getting too much loss in this mixer, or we have an amplifier transistor problem, class C it looks like. We have a class C amplifier problem with the local oscillator frequency coming in. I know this is accurate, okay? And I also know this is accurate. How I know that is because we're getting the correct frequency, which is the mix down, the difference being amplified through this stage, and we're getting it on the scope. It's just at a very low level because we're not getting proper attenuation. The circuit is banging it all the way up to have full power, but it's not being provided. Anyways, and that's what the detector feedback is for. Is it forms a loop to keep the output level regulated. So since this isn't providing enough current, we saw that when we test this probe here, we saw that it dropped down all the way to near 0, like there's no RF. So as a response, the DAC, or this op amp that the DAC is connected to, slams all the way top. So, let me say I think that's over here, but the point is, that's what it does. It's got too much error offset because we're not getting enough gain through this stage. Now, why are we losing gain is still yet to be determined. We're either losing it here, we don't have enough of it here. I doubt it's here because this passes all 3 bands and it works fine. The other upper 2 bands work fine. So this works, and this works. However, this is not working. We're losing too much gain. And that's what we need to figure out. We need to find out why. And the problem is, I'm pretty sure I'm going to have to borrow a good oscilloscope so I can look at this frequency and look at this amplitude to make sure it's within spec, because it does give you that spec in here. And check it in here, make sure there's not enough loss in this mixer, which is right here. Now, this mixer is still available new. I can buy that and replace it, assuming that's my problem. We are getting gain through this stage, but my scope, even if my scope can't see the 800 megahertz, the mix is happening at this point here. I should be able to probe it right here and see the difference. And it should be the 455 kilohertz. It will be weak, but I should still see it. I can't see it. Even with the scope turned all the way down, it's not visible, which means the output level here is way too weak. Why? Good question. It's the next day, and I've been studying this a little more. So my theory of losing gain through this superhet stage may not be the case, and here's why. So we were probing this contact point here, which is like over here, I think, but it's right off this detector diode setup. So, but if we look closely here, the 20 dB amplifier is the only thing that's in the automatic level control servo loop chain. So automatic level control, when you program the amplitude setting on the front, it ensures that the RF level output is a given constant. And it checks that through this servo loop. And if this is off, because your load conditions are going to vary over here a little bit, right? And when it does, the difference comes back to this amplifier stage, and it drives it right back out. And what the way it works is it drives the load on the 20 dB input side. This is the input side going to the amplifier. It will vary the RF level going here to keep the RF level going out there stable. It's a servo loop. Now, the superhet circuit is not part of this loop. So what that effectively means is when this thing, let's say if this has 10 dB of output on it, 10 dB of level, the output from this circuit still needs to be 10 dB going out, and that's why this adjustment is here, because this thing just runs open loop. So the gain going in needs to equal going out. So if we have 5 dB coming in here, we need 5 dB going out there. You know what I mean? So that's how this circuit works. So as we've seen several times now, when you go into low band, what that means is it kicks on the 15 volts to this circuit, so this circuit gets energized, and then it switches this network over so the RF goes through here instead of straight across. And that's when we see this signal fall flat on its face. So that means there's a couple of things could be happening here. Either this amplifier is overloaded, so there's a RF short somewhere in here, either by the mixer or one of these passive networks that's dragging this amplifier down to where now that the servo loop can't compensate, so it pegs to one side, the error response. And we saw that with monitoring this detector. It falls to almost zero when this thing goes to low band. So something is either pulling a very heavy load here, or this amplifier stage does not have the current handling capability anymore. Maybe there's a resistor that's way off value or something. Although I do vaguely recall checking the resistors here, but we'll go through it again. So it's one of those, it's that scenario, and that is this circuit here, I'm pretty sure. So I'll double check all of that first. The other thing it could be is, remember on the input side, we've got more switching networks to switch filters in and out. So it's possible that when this thing goes into low band, the amplifier is falling on its face, not because there's too much load here, but because there's some switching situations going on over there that's causing the RF input to fall way down. So it's one of the two situations, and how we're going to figure that out, I think, is after I verify all the resistors are good here, what I'll probably do is come up here somewhere and disconnect one of these components, which will isolate the superhet circuit away from the rest. So that means my RF level, if this is the problem, my RF level should return because there's no longer any load on this output. Because remember, in the mid and high band, we have proper RF coming out. In theory, anyways. I won't know until I get a tiny SA spectrum analyzer. So that's what I went ahead online and bought. I bought one of those little cheap Chinese spectrum analyzers that I can connect in here to try to look at decibel levels and frequency levels and stuff like that based on what's going on, because I'll find this problem. It's in here somewhere. So that's what we're going to do. We're going to disconnect the load off of this first through the superhet to make sure that that is not our problem. Alright, so I started further up the chain. I disconnected it right here, leaving all of these other little odds and ends in the circuit. Same problem. We've got no RF because we're pegged all the way up here. You got to remember this detector circuit is negative going, not positive going. So if you're up here, that means you've got no RF. And we're uncalibrated still. So that's not our problem. It's not the mixer. It's further upstream. Alright, so I pulled this capacitor right here, which is C254, which separates the entire superhet stage with the exception of this switching network. Well, guess what? We still have the same problem. So we just effectively ruled out the superhet stage. So I was chasing my tail in here when this is not the problem. We're losing RF here when switching to low band. So either our problem is in this, or this switching network could have a leaky pin diode, or we're having a problem up here where we're losing RF on the input side of the 20 dB amplifier because we've got some issues going on there. It's hard to say, but we definitely, we're chasing our way backwards. We're working our way back. And I've been on this thing for too long. I got to make a correction on my previous point here. I was testing this point there, I'm pretty sure, which is here, which is why it's being driven high when I'm in the low band, is because this is the error amplifier output. So this was swinging way high because it was trying to push as much RF as it possibly can through the 20 dB amplifier. So regardless, the fault is still the same, whether I'm probing 8 or I'm probing 6. Point is, I'm looking at the error output level, and it's way, way high. So I tried it without this installed, same fault. I tried it without this installed, same fault. So that rules out the superhet stage. I'm having a hard time believing that it's these pin diodes, because then it would affect all bands equally. I could remove them, but I'm inclined not to mess with those because I don't want to throw the calibration off, because there's no documentation on how to digitally calibrate these, because it's not possible. It's done at the factory. So I don't think it's the pin diodes. Our RF level is on test point 4. I have a feeling if I hook a tiny SA to that, it's going to fall on its ass, because I don't think it's a load problem. I think this amplifier can't keep up with the low band because we've got something going on over here as well. So again, the superhet is not in the servo loop unless the servo or the superhet drags down the servo loop's line, which we disconnected it here and here and it didn't do that. So that is not our problem. Let's look at this servo loop circuit a little bit here. So I was testing this point earlier and it was being driven high when I was in the low band. So what does that mean? Well, this amplifier, this is the servo loop, because there's your feedback. It's right here. So then, because this is driven high, we're getting a high voltage here. But if we follow all this crap, that means not only that, we're gonna throw the unlevel error on the microcontroller, which we are, and that's this guy right here, because I was measuring it. It throws the unlevel control. Actually, no. It's 310A, which is down here. So it was throwing the unlevel control, which it is. If we follow this circuit, it kind of goes up here. So the higher this is, the more RF, the more it forward biases these two diodes, pin diodes, and allows more RF to come through. But because of the way the feedback circuit works, if there's too much RF on this side, it'll come back and it'll cause this to pull down a little lower, so it's not as high, which backs off the voltage here, which lets less RF through. So we have a gain servo loop. It's like an automatic gain control, AGC. We have an AGC here, and the AGC is swinging way off because I don't know why at this point. So either we've got a band switching problem over here, and we're not getting enough RF on this point, or we've got a load problem somewhere. I think I just found it. Look at that. I'm forward biasing one of the pin diodes. It's open. It is CR104. Wow. And that's the input coming directly off the VCO. We're barely getting anything through that diode. The pin diode is open. And that's this guy right here. And you know, it makes sense because I found this because what I was doing was I was looking at this circuit here, and if we look back at this frequency selections thing here, so we know these two upper bands are working, but the lower band's not, and the only thing that's switching that matters here is mid L, which is this signal right here. But it also switches this one, and this circuit is working. So what happens is when this thing is in the middle and upper band, this thing gets pulled low, which allows the signal from the synthesizer to come in this way. Okay? However, when we're in the lower band, which is the one we're having a problem with, this gets clamped off, so the signal doesn't come in through here. Instead, it comes in through here. Because mid-L goes high, positive 15 volts, which feeds it, and it forward biases CR104. So the RF will come from the VCO into CR104. So I decided to check that. Sure enough, it's open. Wow. It's open. CR104 is open. Christ. Okay, so there's our problem. Now, does this solve our problem? I don't know. Let's find out. I could be making a fool out of myself because I really don't know. So let's turn this on. We're just going to leave it to defaults. There's our error signal coming out. We're in the mid band, so everything's good. As soon as I type in, 244 megahertz, it's going to drop off. Yeah, just like that. Now, watch this. I'm going to take my pair of hemostats here, and I'm going to try to short this diode. Don't do this at home, folks. Wow. Look at that. So if I short that diode, I'm trying to get this on camera. Shorted. No more uncal light. Yep. That's it. CR104 is open. Alright, where in the heck are we going to find that? Because those diodes probably aren't made anymore. So you know what I'm going to do? I don't know if this is going to work, but if we look at the switching network for this circuit, we've got 4 diodes shunted to ground. It probably won't kill me if I stole one of those, which are these guys right here. I'll probably go ahead and just steal one and move it over here temporarily and see what happens. But that's our problem. God, it took me forever to find that. Yeah, look right here. It literally just came apart. So that makes me wonder if this thing had too heavy of a reverse bias applied to it when we lost one of the rails. Because remember, we lost a rail. So it's entirely possible that when we lost that rail in the past, it blew this diode up. That makes a lot of sense. That's the only thing I can think of. But yeah, that sucker's open. Yeah, of course. It's dead. So, and these are internal Fluke part numbers, house numbers. There's no specs. We're gonna have to roll with our own. We're just gonna have to go on DigiKey or Mauser and start looking up some pin diodes and try to match the specs of the VCO and stuff like that. There's a lot of variations of this. It's gonna take some experimentation to get it right. I'm thinking about just borrowing one from over here because they're the same exact pin diodes, and these are surface mount soldered, by the way. So yeah. Alright, so I stole one of the pin diodes from over there. and moved it over here temporarily and put it in the proper biasing position. So, will it work or will it not? Let's find out. Hey, we're not getting that 10 code over here now. We're going straight to the oh man, that's so awesome. So, okay, frequency 245 megahertz should work, and it is. Let's go down one. Actually, that's 245 kilohertz. Well, 245, it's fine. There's no errors. No error? Yeah. We're working. It's working. It's working. It's working. Oh my god. A damn pin diode. Alright. 455 kilohertz. Alright. Now comes the fun part. We'll get you out of there. We're going to connect you over here. We're going to put you on the output right there. And I got something. So I don't have a dummy load, so this isn't going to work right. So let's... Oh, yes. Oh, yes. Yes, yes, yes. We're working. Now we're going into uncal because we don't have, anyways. So it's working. It's working. We have a signal. And that is a strong signal. We're getting what? 2, 4, 5 volts peak to peak? It's working perfect. It's working properly. So, okay, let's test. Let's turn the gain down a little. Let's test. We'll just take you to 10 dB. Internal AM. Yes. The AM modulator's working. Yes. Nice. FM modulation is working. It's working. All it was a pin diode. A pin diode. And you can see it. It literally fell apart because I wonder if the rails blew it apart. So yes, it worked. That's it. It worked. A damn pin diode. Sorry. This is mind blowing. But oh, thank fuck, it's fixed. Alright, so I searched high and low on the internet for this specific pin diode because I was trying to match it up so it matches. And I fear if I replace all of these with a newer type that I'm going to throw the calibration way off than what it already is. So here's the thing though. I'm not using this to calibrate military NASA grade equipment. I'm not calibrating a missile guidance system or anything like that. So it's not super critical. I'm using this to do quick and dirty alignments on AM FM radios or tube type TVs, things like that. So it doesn't need to be super insanely accurate. So with that missing, it still has 3 of them in parallel anyways. It seems to be working okay. And it's working well enough for what I want to use it for. So I think I'm just going to go ahead and put this thing back together. I might experiment with certain pin diodes later. But right now it seems to be working well enough that I don't need to worry about it. And I need to get this thing off my bench because I got way too many projects lined up that belong to me but also belong to other people, so I need to get this off my bench. But at least we troubleshooted it, we found the fault, we moved the diode over there, and it is working. It's working fine. Is it working properly, and is it in calibration? I don't know. And I don't have the proper equipment to even be able to calibrate this thing. But it works. That's the important thing. And there is the total casualty report. So we have all these bad tantalums, and then we had this bad microwave pin diode. So there we go. I think that's going to do it. I'm going to leave this for now because I have to move on to other projects. But finding the exact pin diode is being a little bit more difficult. So a friend of mine found the 1985 microwave semiconductor manual, and there is a cross reference to that specific diode. Unfortunately, even with that particular cross reference number, that you can't find it anywhere. But it does list a line item of specs, so maybe I can find the right spec, get close to it. Not sure, but in the meantime, I'm going to move this out of my way for now because it is working and it will do what I need it to do. So anyways, if you learned anything in this video, I'd appreciate a thumbs up, and don't forget to leave a comment if you have one. Until next time, guys, thank you for watching.